Okay, so it is being recorded now. Thank you, Shivansh. I just saw that it is not being recorded. Okay, so I have just created this circuit and given the power and leakage in this. Now I'll simulate it. Let us see the impact. We see that the power, the dynamic power dissipation is 5.43225 nanowatt, and the delay is 47.0486. Right? Now we'll apply the technique that we use to reduce the leakage to the circuit. And the technique says that you remove this from here and add one transistor there. Then you can use the wire this way, connected like this. Okay, got the point? Or is there anything that we are missing?
So body terminal first.
How we have connected the body terminals.
So, but the body terminal isn't connected to ground.
Shivansh, I'll explain this. We can go both ways. I told you that body terminal in particular, you see this. What is the concept of body terminal that we need to see? I told you initially when we did this MOSFET part, I told you that this is the gate, this is a source, this is a drain, right? Here you have the voltage. Now this body has a certain voltage and this source is always on the ground. When the source is on the ground and the body has some other voltage, then this is N, this is P, this will either become forward bias diode or become the reverse bias diode. To make it neither of them, we actually connect these two so that we can avoid becoming a diode. So either we give it a 0 manually or we connect both of them. This will actually almost behave the same way. So I have connected it to the source with the body.
Okay, sir.
Right? Okay, so now we have added one transistor. Everything is okay? Yes. Now let us see the impact. Let us see the power. Power is 5.43225 nanowatts and the delay is 47.0486. Check the power dissipation. The dynamic power dissipation has increased. It has increased to 5.9597 and the delay has also increased 64.63 3632. Let me tell you what was the initial case. The initial case was that the dynamic power was 5.43. Now it is 5.95. The dynamic power has increased and your delay has also gone high. So you have reduced the leakage, but your dynamic power has increased and your the delay has also got increased. Means the power has reduced. Your output is coming late. It was coming at 47 picoseconds. Now it is coming in 64 picoseconds. So you have reduced leakage. You have increased the size you have increased the dynamic power dissipation, you have increased the delay. So this is your impact of using stacked transistor. Got it? These are all the parameters that you need to take care when you talk about using any technique. That is why I have calculated all the parameters for you. Now I'll use the other technique for you, which is called using the sleep transistor. For using sleep transistor, this. Okay. And now let us re-simulate it. Now the leakage, now the dynamic power is 5.97 and the delay is 47.51. So the delay in the previous case was 47.04. Now this is 47.51. Delay has increased, but not the way we have increase in the stack transistor. And in sleep transistors, we have, in the stack transistor, we had the dynamic power dissipation 5.95. And in sleep, we have 5.97. So there is slight increase in the power dissipation of the dynamic power also. So we have seen both the techniques. What we have noticed that the size, okay, the size of PMOS is way higher than the NMOS. So in this case, the size of the device will increase more than the size of the device that increased in that previous case. So the device size will increase in both cases. The power dissipation, which is called dynamic power dissipation, will increase in both cases, and the delay will increase in both cases. Now I'll take one case where I use both sleep and stack in a circuit in a single go. The power dissipation is 6.61 and the delay is 65.019. In this case, it is very, very high power dissipation, dynamic power dissipation, and the delay is also higher than the previous cases. But the leakage will also reduce in this case, that is for sure. So we have implemented the stack technique, we have implemented the sleep technique, we have implemented the stack sleep both, and we have seen its impact on the leakage power, on the dynamic power, and on the delay, right? So this technique in particular is used. This was the first technique which was implemented for reduction in the leakage power. When you will read the books or the research papers about the reduction in leakage power, which is a very important case, then you will see that stack, and even till today, when we read the research papers, we see that many of the researchers are still using this technique only in a very simple manner. Uh, what is the advantage of this technique? That this technique does not calls for adding up many transistors. It adds up only one transistor in series and one as a stack, one transistor as a sleep. These technique has another advantage that you can implement stack and sleep in a separate manner also, depending on the choice of your circuit. But I again say that please take it with a pinch of salt. Do not run behind the simplicity of any technique. Sometimes it may harm your dynamic power more than it would have added up to your leakage, right? So please use this technique wherever and whenever it is required. Now let us come to the other technique, which is called using high threshold transistors. I'll show you one example of high threshold transistor also uh, in this case. What is the meaning of using high threshold voltage and how does it impact the leakage? Let us see. Okay, we have dynamic power in this case. Right. Let us see, the delay will not work in this case. What is the power dissipation? 2.14874, which was the actual power dissipation of the inverter, leakage power dissipation. Now what I'm going to do is I'm going to delete this NMOS and I use a high threshold NMOS. This is NMOS HVT, high threshold voltage. Please see the power dissipation. Please notice 2.148, and when you simulate it again, 0.745 picowatts. But the question is, if it is that simple that you need not to increase the size of the device, you need not to do anything, and your leakage is reducing, why don't we use it? Remember, without using this device, my the delay of my circuit was 47.048. And now what is the delay in this circuit? For delay, I need to give the switching voltage. Please see, the dynamic power is 5.662 nanowatt and the delay is 69.93, which was actually initially it was 47.04. Means the delay increases drastically when you use high threshold devices. So high threshold devices are used in case when you do not have to use when where you do not have any performance based condition and you just have to reduce the leakage power without increasing the size of the circuit. I repeat, in case where you do not have to increase the size of the circuit and you need to reduce the leakage, you cannot add on any transistor, but the performance of the circuit does not matter. In that case, you can easily use high threshold voltage, but you see this is also one effective measure to reduce the leakage power of the circuit. Now there is third case, which is called reducing the VDD. I show you one more case. What will happen if I use LVT? It will increase the leakage and improve the delay. See, This is your LVT. If I implement this, your initial delay was 47. Now the delay is 32. The performance has improved. If you see, the performance has improved. But what about the leakage of the circuit? For leakage, I'll test it. I'll give 0 over here. The initial leakage was 2.14 or 9. Yes, initial leakage was 2.148 picowatts. Now, what is the delay? What is the leakage with low threshold voltage? It is 28 picowatt. Look at this, 14 times increase in leakage power. Your performance improves, but the leakage power increases drastically. So it is it needs to be seen with a very care that whether you wish to use the low threshold voltage or not. In very less cases, when we actually require the very high speed circuit, we use the LVT transistors. Otherwise, we don't use them. Now I'll get back to standard threshold voltage. And I use the concept of lowering the VDD. If I'm working on a circuit on 0.7 volts and the power dissipation is 2.148 and I use the VDD 0.6, the power dissipation reduces. Reducing the VDD is a very simple way, because in this case, you are implementing the process of using this V cross I. You are using this V cross I for power. Two, if you reduce the V, because V is directly proportional to I, if you reduce the V, the I will reduce and automatically the power dissipation will reduce. So reducing the VDD, it's a universally accepted technique, but please remember, if you reduce this to reduce the leakage power, the delay may go haywire, right? If you check, if you will do simulation yourself, you will see that there is a huge difference between the delay given by the device at 0.6 volt and 0.5 volt, and probably it will not work at 0.4 volts, right? So what we have done so far today is that we have talked about our circuit. We have talked about the inverter circuit in case of the various leakage control techniques. We have used a technique of stack, we have used a technique of sleep, we have used a technique of stack sleep, high threshold, and reducing the VDD. And then you can always find the power dissipation and leakage, can multiply them and can see the PDP of the circuit, which is called power delay product. And you can see whichever is less is a better technique. So these are the circuit techniques. There you see that what is the impact of delay, what is the impact of what you call the dynamic power, and what is its impact on the size of the device. Now, what we are left for that roadmap of today is that we need to discuss a few concepts of delay. We'll discuss them and then we'll close this lecture. Till now, if anyone is having any doubt, please let me know. Please tell me if anyone is having any doubt still here. I'll explain you. Even if you think like it's a random doubt that I should not ask, please ask, because once you will ask it, the doubt will go forever. Otherwise, it will remain in your mind. Don't mind that I will ask the wrong thing and this will make fun of me. These things doesn't matter. Your doubt should not remain in your mind. That is something which is very important. Right. So I start with the concept of transient response. Okay. So there you see the concept of transient response. From Monday onwards, we'll be studying the memory in any case. We will not study any more circuits. There are many things in this PPT that you know, because we have done a lot of things. You have seen a lot of things which have been done practically. I can show you many things over here, but we'll concentrate on the transient analysis. Okay. This says that the DC analysis tells us we have this. Can you cross it? This pen is not working. Okay. This DC analysis tells us that V out if V in is constant. What does this first line means? It means that whenever you use the DC analysis means the same thing that you do. DC analysis means the same thing that you do in your leakage power analysis. It is talking about that. You have a V in, you have a V out of an inverter. You will see that in this case, V out and V in. If we have 0 over here, the V out will be 1. But when it is talking about the V out, it is not merely talking about the voltage over here. It is talking about the power dissipation. Because in the DC condition, the current is called the leakage current. There is some problem with this PPT. The pen is not working correctly. Right? Can I use the other way around without using this? Okay, this way. And the input is usually considered to be a step or ramp from 0 to VDD or vice versa. You please see that whenever you use a dynamic pulse, we consider that from 0, it moves to here instantly. But we have seen in our simulations that it is not the case. Practically, when a wave goes from 0 to 1, this goes like this, and it goes from 1 to 0 this way. Why this happens? There is a general question that student asks, that why there is a difference between 0 and 1. This is because when you go from 0 to 1, the transistor which has to make it from 0 to 1 actually gets charged or discharged. And many times I have told you that the MOSFET behaves like a capacitor also. Whenever you charge a capacitor, it charges like that and discharges like this. So that is why your charging is this and discharging is this. No pulse practically is of this shape, this straightforward. No pulse is of this shape. Every pulse, if you zoom it, is practically of this shape. So input is usually considered to be ramp from 0 to VDD, right? I'm talking about the transient response of the circuit. Then you please see inverter step response. We have seen the step response of inverter in our PPT. I will not go to this equations because when I'll teach you the MOSFET current equation, then I'll come to this. Now, what is the definition of delay? This is a usual asked question in the interviews, that what is a delay? Please see this wave shape very carefully. This is the input and this is the output. It is showing that this is V in, this is V out. There are certain definitions, which is PPDR, rising propagation delay. Rising propagation delay is, what is the PPDR and what TPDR? TPDR is this and this. Means 50% of input coming down and 50% of output coming up. So this is called TPDR. Propagation rising delay. Rising, what is rising? Output is rising. Input is declining, falling, but output is rising. So this is called rising propagation delay. The rising word means the output is rising. Then there is a falling propagation delay. See, your input is going up and output is coming down. So the difference between this and this is falling propagation delay. Now the valid question should be that how these markers have been created. How these markers have been created? These markers have been created in such a way. You see, this is 0 volt, this is 1 volt, this is exactly 50%. So 50% of input up and 50% till 50% voltage output down. When the output comes down to 50% with the rise of 50% of the input, then the total delay between these two things is called falling propagation delay. The input has gone 50% up, the output has gone 50% down. It may happen that if this output comes down like this, for example, then we would have taken this point and we have told that this is a TPDF, right? Then there are two more things in delay, which is called TPD-TR. Even if you know what is delay, even if you know what is power, but there are certain theoretical definitions which you should always know, because these are usually asked in the interviews. Now, what is the average propagation delay? Average propagation delay is this TPDR plus TPDF divided by 2. This is the average propagation delay. What is the rise time? Rise time is when your input goes from here, this goes from there to there. This is rise time. Means rise time is from 20% to 80%. When your wave shape goes from 20% to 80%, this is called rise time. In many books, you will see that this number is taken as 10% to 90%. So this depends on the different sort of approximations that you take. But in this case, it has given 20% to 80%. That is why it is taken as a rise time, right? So there are four definitions. One is rising propagation delay, where the output is rising, input is falling. And there is falling propagation delay, where output is declining and input is rising. There is rise time, where your input rises from 20% to 80%, and there is fall time when your output from 20% to 80%, and there is fall time when your output goes from 80% to 20%. And then there is an average propagation delay, which is this PDR, rising propagation delay plus falling propagation delay, divided by 2. That is how we talk about all the definitions of delay. These are very important for your interview perspective. So please remember these definitions. Even if you know about how to find delay in your simulator, but these are the terms which are usually asked in your numericals also. So please remember them. So we have taken that there's a fall time. I told you that when it goes from 20% to 80% to 20%, this is called fall time. Now you see there is one more thing. What their definition, that what is called rising contamination delay, falling contamination delay, and average contamination delay. We know from the simulator that what is a delay, but we hardly know that what are these definitions. Rising contamination delay is when your output is crossing VDD by 2, when your input is falling output crossing VDD by 2, and the average of them is called average contamination delay. So these definitions you should remember for your interview perspectives. This is the simulated delay of the inverter. We have seen it multiple times. This is the input wave shape. This is the output wave shape. So in this case, this is called TPDF falling. This is called TPDR rising. It is 66 picosecond. It is 83 picosecond. This value may depend on the kind of a circuit you are using, the kind of a transistor you are using, the kind of a technique you are implementing, and so on. So take it with a pinch of salt that whatever is given to you in this PPT may not be true for your circuit, but you please implement your circuit yourself, and then you see that how much the delay, this TPDR and TPDF that you are getting in your circuit. However, in any of your projects, it will not be asked that how much TPDR or TPDF you are having, but usually people are interested in knowing that which is the higher of both. So that, because that defines the delay of your device. What is the delay estimation? Delay estimation is that we would like to be able to easily estimate the delay, not as accurate as simulation, but what if means you estimate the delay. They are talking about the theoretical estimation. So the step response usually looks as the first order RC response. There is a case when they talk about that showing this MOSFET as an RC circuit. I will also in the next lecture I will also tell you that how the MOSFET can be taken as an RC circuit. Probably this PPT has given them. I'll show you. Yes, this way. This is your MOSFET, and this is your MOSFET is shown as a resistance and a capacitance. So I will show you and I'll explain you that how this RC delay model is created with your NMOS only. And with this NMOS, NMOS and PMOS. You see, this is the model for NMOS. This is a model for PMOS. And using this NMOS and PMOS, we can create the similar model for inverter. This is your fan out of one. One inverter is driving the other inverter. Don't worry. I'll show you all these theoretical concepts in your next lecture on Monday. Till then, let's stop it here. Now we'll meet on Monday. No class for tomorrow, Sunday. Thank you very much. Good night. And please drop me as a message if you have any doubts for today's lecture. We are stopping it here, right? If you have any doubts, please ask me in the group, and I'll take on your request. Yes, please go on.
Sir, actually, I have a